Start this here. Big week this week. Why? Oh boy. Well, this will be a rude awakening. If you missed it, we have test 2 on Thursday. Blah. No, I know you guys have been studying for it. I was kind of slow to reply to stuff this weekend, which I'm kind of embarrassed about, but I wasn't feeling very well. So test number 2 is on Thursday. And I gave you that practice document. And no, I still haven't posted the solutions with the T table. I did post the solutions with the Z table. I'll update the ones with the T table. But you can use either on the test and it doesn't matter to me. I'll know either way. Okay, so we're covering just these topics, just these. When I give you, it's easy. Hypothesis testing, confidence intervals, blah, blah, blah. One sample proportions. Oh, hey, where's the pointer? One sample proportion, 2 sample proportions, chi-square goodness of fit test, 1 sample mean, which is what we started last week, and then paired numerical data, which is what we did on Thursday. And then today we're going to introduce the last type, which is obviously not on test 2, but on the final exam, where we have 2 independent sample means that we want to compare. Okay, and so I want to give you a little heads up here. I'm only going to do the categorical data questions for the long answer. Okay, and so there's going to be 3 long answer questions. 3 long answer questions. And I'll take it one step further. 2 of those will be hypothesis testing and 1 will be a confidence interval. Obviously, I give you practice for all of them always, but you'll just have to do 1 for some unknown types. So 2 hypothesis testing and 1 confidence interval. Okay. For 1 sample proportion, that was chapter 5, where we spent a lot of time introducing kind of the concepts of hypothesis testing and confidence intervals. We carry those through all the way through here, right? So we built those skills back here in chapter 5, but also in section 6.1, we did 1 sample proportion again, which I kind of skipped because we were running behind. We have the sample size calculation, which I've promised is going to be a bonus question. There were some assignment questions for extra credit for you to try, and so similar to those, right? Calculate the sample size. Okay. So for 1 sample proportion, we can do a hypothesis test, or we can do a confidence interval, or a sample size calculation, which will be a bonus. For 2 sample proportions, we can either do a hypothesis test or a confidence interval, or both. And for the chi-square goodness of fit test, we only do hypothesis testing. Hey, but Emily, you said there were only 2 hypothesis testing questions. It's being narrowed down by the minute here, right? And so, all right, one of those has to be this one, of course. All right, of course, there's going to be 1 of each of these. All right, can kind of figure out what's what here. Who's who in the zoo? Then, well, what about all these? I practiced these too. I know you did. So what I want to do is, I think there's, I want to do about 6 of them where you just read a question blurb and then you tell me what type of question it is and if it's one-sided or two-sided, if it would be a one-sided or a two-sided test, because I know that's a sticking point and that's difficult, right? But once you've got it, you've got it. And so, right? And so it's going to be kind of a fire drill version or a mad minute of what type of question is this, right? What type of question is this, right? And so here I'll do on this side, and it can be any one of these, right? Read, I'll do roughly 6. I can't remember if I did 6 or 5. Question?
Yeah, can you please go over how to determine if it's one or two-sided P real quick?
Yes. Let me just write this down, you bet. So read approximately 6 question blurbs. Blurbs, is that a technical term? I don't think so, but I think we all know what it is. You've got this and this and this. So read roughly 6 question blurbs and identify the type of question. And if it is a one-sided or a two-sided test. Now, the reason I do this is because, right, it's one of those disconnects, because what do you have to look at? You have to look at the alternative hypothesis. We're comparing some mean or some proportion to some number, or we're comparing 2 proportions to each other. But in your null hypothesis, you always have an equal sign, right? Regardless of the scenario or regardless of the question type, you always have an equal sign. In the alternative hypothesis, okay, this is where we decide if we have a two-sided test, right? So not equal to here makes it a two-sided test because I don't care which tail it goes into. In fact, I'm concerned about both tails, right? A two-tailed test or a two-sided test. And so this makes it, how do I didn't give myself enough room here. You know what? Go crazy, give myself another virtual line here. This is a two-sided or two-tailed test if you prefer. Right. If you have less than or greater than, that makes it a one-sided test, right? And that's reflected in the p-value later, right? Which area in the tail do I want? And so these are both got squiggly brackets all over the place. These are both one-sided tests. And it's reflected in, well, if I have a two-sided p-value, then I want the area in two tails, right? I don't care which direction it's going in, right? I'm concerned about both of these areas. Should be symmetric, but man, I did a bad job. If I want to know if something is less than something else, and I'm keeping it generic on purpose because we could be talking about one sample proportion, how 2 sample proportions compare to each other, right? Or how one mean compares to a value, or how the differences, the mean differences compare to 0, right? But regardless, this is what it's going to look like. So if I have, if I want to know if it's significantly less than something hypothesized, then I'm only concerned about this one area, right? The lower tail, right? Less than. Whereas if I want to know if it's greater than some hypothesized value, my p-value is the area in the upper tail, right? And that's why in the labs, if you want to show that something is greater than something else, right, then you have to find the area in the upper tail, but software only gives you the area in the lower tail, so that's why you have to do the 1 minus. Or multiply by 2 if you have a two-sided test. Right? So it's all baked in. Okay, does that?
Yep.
Cool, nice. It's one of those tricky parts, but then once you see it, I guess you can't unsee it. It's one of those. Right. It's like, why was that so hard before? Well, it was, I know it is. Okay. Little bit of review. Last week, we started analyzing numerical data, which meant we were analyzing a mean or, well, we only did one ultimately last week, but for review, oh, any questions about the test? So kind of 3 long answer, 6 short answer, and then that's it. Yeah.
Is this kind of more for the final? Is the final cumulative or is it?
It is cumulative, yeah, with focus on the later parts. Yeah. Yeah. But it is cumulative. I cut as much probability as I can. No tree diagram or anything. If I can help it, we'll have to check. All right. Little bit of review, just because we're building on it today. We started analyzing I can't decide if I want to do analyzing numerical data, right? Which means that I'm interested in the average or the mean. Right? And where we started was we said, okay, well, what if I just have one sample mean and I want to compare it to some number? Is it less than 32 or is it greater than 54, whatever, right? And so whatever, what can we do? Well, if we have one sample mean as the type of question, right? Then the information that we need, right, is I need to have the mean of our sample, of course. So I need to have some X bar. I need to have the standard deviation of that sample. And for me, that's a dead giveaway that this is going to be a means type of question. If I see the word standard deviation, then I know, okay, I can't calculate the standard deviation of a categorical variable. And so then we can have the standard error, but not the standard deviation. And so this is kind of my go-to guide of determining what type of question it is. And then I can dig deeper and figure out which type exactly for the means, but at least it narrows it down. And I need to have my sample size, of course. I always need a sample size. And some value that I want to compare my sample mean to, right? And so I need to be given some sample mean and some value that I want to compare it to. Okay. From there, I can set up my null hypothesis, which is that mu is equal to mu naught, right? I have to assume that the mean is whatever value I want to compare it to until I have proof otherwise. Kind of wanted to keep this on one page, but it's not looking good. Then, so I'm not going to write out the alternative hypothesis because it can be mu is not equal to mu naught, mu is less than mu naught, mu is greater than mu naught, and that depends on the question, right? But we're still just comparing these two values, and so it's not worth writing it down. And that's why it's not on your formula sheet either, right? I just have your null hypothesis, and then your alternative is based on that. Then what do? If we're doing a hypothesis test, then I calculate t. So t is going to be my point estimate X bar. How far is it from my hypothesized value of mu naught? And so X bar minus mu naught divided by the standard error of X bar, which is S over root n. This is, of course, on your formula sheet. So it's not something that you have to think about or anything, but you do have to be very comfortable using your formula sheet because it has all the information there, and I am trying to guide you in the right direction. But that takes a lot of practice, right? Getting used to the formula sheet. Oh, it's on there. Don't need to remember every little thing. Once I have my t, because we're doing a paper test, right? And we don't have Excel, we have to use the table, which means I need to find my degrees of freedom. So the degrees of freedom is n minus 1. Yeah. Once I have my degrees of freedom, right? If I don't find the exact degrees of freedom on the table, I have to round down, right? Otherwise, we're saying I have a bigger sample size than I actually do, and that's really bad. See, it's easy. Hypothesis testing, look at how little it is. Well, not quite. Conclusion's a big part of that, right? But the conclusion is always the same, right? Depends on the p-value, which you find from the table or software. And then the alternative thing we can do is make a confidence interval. Confidence intervals always have the same format, right? Our point estimate plus minus our critical value, which in this case is a t star at n minus 1 degrees of freedom times s divided by root n. That's really nice, right? We're used to seeing standard errors that are different depending on what I'm going to be doing, but for means, they stay the same, and so that's kind of a relief. Okay. Then, on the flip side, what if I have two paired samples, right? And so there's some way that I can say that, well, this observation and this observation in each sample, they should be linked. Maybe they're measurements on the same person, which is usually the case, kind of a pre-score, post-score situation, right? And so now I have two paired samples. Then I'm analyzing the mean difference. Right. So then I'm going to have sample 1 and sample 2 in my spreadsheet. But then what I do is I calculate the differences, and I can find the mean of the differences. And what we're going to do is just put a little subscript diff on there just to highlight that you know it's the differences, or a little d if you want. The standard deviation of the differences and n of the differences. This is the same list of information, right? In fact, we apply the same techniques, but in a simplified way. It's harder because we're talking about the differences, right? The mean of the differences, but the mean of the differences, I'm only concerned about how it relates to 0, right? A difference of 0 says there's no difference between these groups. And so my null hypothesis is that mu diff is equal to 0, right? We're always going to compare our point estimate, so the mean of the differences, our sample mean of the differences, how does it compare to 0, right? Beyond that, these steps are all the same, except we use the information from the differences. So t is going to be x bar of the differences, technically minus 0. I can't remember if I have minus 0 on the formula sheet or what. S diff over the root of n diff. But that's the same, right? Just throwing little diffs everywhere. Your degrees of freedom is n diff minus 1. And then your confidence interval, x bar diff plus minus t star at n diff minus 1 degrees of freedom times s diff over the root of n diff. Nice. We've just written out the formula sheet, right? And so knowing all those components, but we kind of talked it out together. And so I find that helps at this point. Okay. I'm just gonna go and see if I have -0 or if I just have the X bar diff on the formula sheet. Who knows? How am I to know? Let's see here. I do have -0. You don't have to, it doesn't do anything. But it highlights you're seeing how far this difference is from 0. Okay. Okay. Call that the end of our review. So today we're going to talk about, well, what if I can't pair my observations in sample 1 and sample 2? Maybe there's there's nothing to pair them on, and that's totally fine. In fact, that's the most common scenario, the one that we're about to talk about. Okay. In general, when we're using t as our test statistic, we usually just call them t-tests. And so, when you're using a hypothesis test that uses t, which means you're analyzing numerical data, then we just call it a t-test. So out in the real world, right, someone's going to throw in your face, well, couldn't you just run a t-test? It's all kind of in an arrogant way usually, and you know what to do, right? It's a hypothesis test that uses t. And so the most common t-test that we run is for 2 independent sample means. Okay, so I'll write that down here. The most common t-test which is a hypothesis test with t as the test statistic. Just so you're good with the lingo. So the most common t-test we run is a 2 independent sample means t-test. Is a 2 independent sample means t-test, which is section 7.3 for us, difference in 2 means. So in terms of the type, instead of saying 2 independent sample means t-test or 2 independent sample means, I guess I did call it that. Independent, how do I spell independent sample means, or 2 independent sample means is what I call this type of question that we're about to do. Okay. So now I have a spreadsheet again, and I have variable 1 and variable 2, and they're both numerical, and I want to compare the means of these 2 things. These 2 things could be averages, so any 2 averages. The average sales of I don't know, employee 1 and employee 2, right? The average, mine are all sales really, I don't know. The average revenue at location 1 and location 2, right? You want to compare these. And so now we want to compare 2 independent groups. Sales at location A versus B, for example. Oh boy. Now we've got these independent groups. Drug A, drug B. As long as what we're measuring is numerical, then we can use this method. We've seen this problem before. Oh my gosh. Sorry, my cough drops are huge. So there's Buckley's inside, I guess. My mom's like, take these. They're so old, but they do work, so. Yeah, I'll work my way through them. Sorry, guys. Let me just think on it for a second. I'll write it. We've seen this scenario before, right? When we had two sample proportions, now we're overwhelmed with information. Because I'm gonna have a mean for sample one, a mean for sample two, a standard deviation for sample one, a standard deviation for sample two, a sample size of sample one and a sample size for sample two, and they're not even necessarily the same, which is a cool feature of the two independent samples. X1 bar, X2 bar, S1, N1, S2, N2. I'm just gonna scoot this down here. Doesn't matter which one you assign to group one and group two, as long as you're consistent, right? And so we've seen that before as well. Now, what's really fun about two sample means is the point estimate is always the same and the standard error is always the same, regardless of if we're doing a hypothesis test or a confidence interval. And that we've seen before for means, and it stays true. Our point estimate is going to be X1 bar minus X2 bar. Guess I don't need brackets around it yet. This is a difference in the means, right? And that's what we said. We're going to analyze the difference in two means. Okay, so this is going to be our point estimate. The standard error, of X1 bar minus X2 bar, which is our point estimate, is going to be the square root of S1 squared over N1 plus S2 squared over N2. Square rooted.
So it's only S1 squared, not N1.
S1, yeah, exactly. So the square is only on the standard deviation. So we've got addition in here, so we're not actually allowed to do it. But if we think about S squared over N, I could simplify this and I'll delete this because you don't need to worry about it. The square root of S squared over the root of N, well, the square root of S squared is S over root N. Hey, we've seen that before. Well, it's kind of like a mashup, right? We've got two samples. Because I've got addition in here, I'm not allowed to break up the root, but the idea is the same as what we've seen before. So it's only on the S. And don't forget that square. Common mistakes I see are you've forgotten to take the square of the standard deviations, or by the time you've done all this work inside, you forget to take the square root, and that'll mess things up as well. Usually your t gets really, really big if you forget to take the square root, right? So that's kind of a good check-in point. So this is the standard error of the point estimate, just generically. So now we can talk about, okay, a t generically is going to be a point estimate from the hypothesized value, right? And just as before, if I'm talking about the difference between these two things, then what am I going to hypothesize about? Well, my null hypothesis will be that mu1 minus mu2 is equal to 0. I'm going to assume that they're the same until I have proof otherwise, right? So my hypothesized value is 0. A hypothesized difference, I guess, is 0. Okay. Generically, T, or any test statistic, right? Z and T behave the same way, they just take different values, right? So the point estimate minus the hypothesized value divided by the standard error of the point estimate. This is one of those things. So I introduced this in chapter 5, but I don't expect it to sink in. But now we've seen enough of them to say, oh, that's the layout of all of these T's and Z's. It is, right? So that's kind of cool. We're ready for it now. In our case, the point estimate is x1 bar minus x2 bar. How far is that difference from 0? In terms of the standard error, which is that big mumba jumba. But if you're using the store function on your calculator, once you've calculated it, just store it, and then you can just recycle it, right? I don't expect you to calculate it twice or anything. S1 squared over N1 plus S2 squared over N2. Huh. We did it. What about the degrees of freedom? The degrees of freedom is there's a huge formula that software uses, but we're just going to use the smaller sample size minus 1. There are some textbooks that use N1 plus N2 minus 2, but I don't want you to use that. I want you to use the minimum of N1 minus 1 or N2 minus 1. This is just a mathy way of saying the smallest sample size minus 1. Oops. The minimum function, right? And then we can do our calculation. We have a sample size for group 1 minus 1 or sample size of group 2 minus 1, whatever the minimum of those two values are, then that's the result. And we'll see it in an example. How about a confidence interval? Same generic layout for a confidence interval. So for a confidence interval, we have some point estimate plus minus a critical value. I'll call it a CV, because it could be a Z star or a T star from the table, or Excel if you prefer, times the standard error of the point estimate. We have all these components. Our point estimate is x1 bar minus x2 bar, plus minus, our critical value is going to be a T star at the smaller sample size minus 1 degrees of freedom. I'm not going to write that down because that's a huge subscript. I don't like that. Times the standard error of the point estimate, which is still S1 squared over N1 plus S2 squared over N2. And that's your confidence interval for the difference in the means right? Interpretation gets a little bit boggy, right? Because now we're talking about the difference in these two means, right? But we'll see an example. I wanted to grab what did we just do? We just made the formula sheet, right? And so here, if I have two sample means, I'm going to copy this, bring it in. Oh. Hello. Where can I sneak this in? Maybe I'll put it up here. So on your formula sheet, same as always, this theoretical distribution, it is what we're using in the background here and here, but it's not something that we need to worry about. So you can kind of ignore that. Be really bad if I didn't have it on there though, for me. But just as a reminder, right? So here we have two sample means. I often emphasize that they are two independent sample means, but you can just call it two sample means. We're analyzing the difference of two means, right? And so here we've got our confidence interval. I'm concerned about the confidence interval for mu1 minus mu2, and then my point estimate, my critical value, and the standard error of the point estimate. Same as we saw for the proportions when we had two sample proportions, I'm going to focus on this version of the null hypothesis, mu1 minus mu2 equals 0, just because that's what I'm using down here in my test statistic. But if you prefer to write mu1 equals mu2, and then how they relate to each other that way in the alternative, that's totally fine. Whichever one you choose. T and the degrees of freedom. Just like that, we're ready for an example. Well, any questions? I'm telling you, we're ready for an example, whether you like it or not. So we're going to work with these this diamonds data set. In case you don't know, the weights of diamonds are measured in carats. And what we're going to say is that 1 carat is going to be worth 100 points, and 0.99 carat diamonds are worth 99 points. And so what we're going to do is we're going to compare point prices because that puts them on the same level. Okay? So the difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the, I feel like the naked is kind of excessive, the human eye, the naked human eye. But does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? So knowing that you really can't tell the difference between these two things, right? It might be valuable to know that, well, is the price of these things significantly different from each other, right? Or here, I'm going to remove this because it's kind of a, here it says if there's a difference between these two, what would that mean? That would mean that your alternative hypothesis is that mu1 minus mu2 is not equal to 0, right, for a difference. But we're more interested in, well, the 1 carat diamonds, are they significantly more expensive than the 0.99 carat diamonds? So I'm going to remove this. Because it bothers me that they have a different question later. This is just some background on how we got the information. It'll be more straightforward on the final exam, I guess. In order to be able to compare equivalent units, what we're going to do is we're going to divide the prices of 0.99 carat diamonds by 99 and 1 carat diamonds by 100, and then we're going to compare the average point prices. Okay. Little diamond on there. Okay. These are the point prices out here. Okay. Looking at the side-by-side box plots, right, we can see a lot of things. There are no outliers, so that's nice. The 0.99 carat diamonds, the point prices tend to be just generally lower than the 1 carat diamonds. And that's why we're going to do this hypothesis test, right? To see, okay, I can see that there's a difference here, but is there a significant difference? In fact, does this 1 carat diamond, this group of 1 carat diamonds, tend to be significantly higher than 0.99 carat diamonds? We can also look at the distributions. And the reason I mention this is because one of the conditions of the test is that we have a normal distribution in each group now. How can we tell if there's a normal distribution from a box plot if there's kind of symmetry in each of the areas, right? And so around the median, this area is roughly symmetric with this one. Now we're going to squint a little bit and be very generous, right? And say this is roughly symmetric with this area, and the tails are roughly symmetric with each other. It's not, I wouldn't say that's truly the case, but it is my argument because I need it to be normally distributed or approximately normal. Here, same thing, I would argue it's roughly kind of symmetric, and so I would argue normality. If we can't argue normality, our sample size has to be bigger than 30, and then we can just assume normality. All right. Okay. The layout of the information is often most telling of what type of question you have, right? I can give you all this information in a blurb, and there are practice questions where it is given in a blurb, right? But if it's laid out like this, then it's going to be a 2 independent sample means question. Okay. And so what we have, if we call the 0.99 carats sample 1 and the 1 carat diamond sample 2, or group 1, group 2, then just looking at these averages, 53.43 is less or is more than 44.50, right? But we want to know if it's significantly more than 44.50, right? There's wiggle room because we have these standard deviations for both groups, and we have relatively small sample sizes. I'll make a note here. Notice the sample sizes are allowed to be different. That's also a telltale sign that it's 2 independent sample means. You can have the same sample sizes, but definitely if they're different, then it's 2 independent samples. And so notice we allow 2 different sample sizes. I think that's kind of neat. And you don't have to worry about collecting the same size sample all the time. Okay. Yeah. I'll also highlight that these data are random sample. That's important for the independence condition later, right? We have to have a random sample, but now each of these samples have to be randomly selected because they each have to be independent within, but also independent between because I'm saying they're 2 independent samples. The thing I'm interested in is the average difference between the point prices of all 0.99 carat diamonds and 1 carat diamonds. So I could write something like mu 99 minus mu 100, right? How does that relate to 0? My point estimate for this value is, of course, the sample means subtracted from each other. So x bar 99 minus x bar 100. what I'm gonna do, so they do go through it in all the following slides, but I'm gonna go rogue. I guess it's an example, it's a huge example. Is there evidence that, I guess I should write it down. Whenever you see is there evidence, that's a hypothesis test, right? So you have to do the full, all the steps. Is there evidence that the, how do I want to do it? Yeah, we can do that little switcheroo. Is there evidence that the 1 carat diamonds have a significantly higher average point price than 0.99 carat diamonds? Okay. I'm gonna grab the information that we have. Because I have a hard time reading from right to left or whatever, I always use the first one as sample 1 and the second one as sample 2. And then I make adjustments to my alternative hypothesis later, like this. Step 1, state the hypotheses. And I think I've mentioned it before. You don't need to actually state what the steps are. As long as you do all the steps, that's fine. But I just like to have it so that you can see that we're just doing the same thing over and over and over again. My null hypothesis is going to be the mu of, I'll use 99 minus the mu of 100 is equal to 0. The difference between these two groups, right? Mu1 minus mu2 is equal to 0. Okay. In your null and alternative hypotheses, I want to see question-specific subscripts, right? You have to use question-specific subscripts, especially if you have a less than or a greater than in your alternative. Then you can't just have generic 1 and 2 because it doesn't mean anything. So now, okay. We want to know if the 1 carat diamonds, which are the 100 pointers, have a significantly higher average point price than 0.99 carat diamonds. So now I need to think about, okay, how does this difference relate to 0 if 100 is always higher than 99? Okay, so then I'm taking examples like, let this be a 1 and this be a 2, right? Something higher than 1. Then I would get a negative number, -1, which is less than 0. And so my alternative is going to be mu99 minus mu100 is less than 0. We know from earlier that if I'm only concerned with that one extreme, then this is a one-sided test. Now we're ready to rumble. Okay. And so a little bit of switcheroo, right? Because if you wanted to talk about the 1 carat versus the 0.99 carat, then you might switcheroo these, but then it makes it hard to read the table, and I find that that's really confusing. So I make my adjustment here, and then I can just use it as group 1 and group 2 as I wanted to. Okay, so here, this is X bar for 99 points. This is X bar for 100 points. This is S for 99 and S for 100, N for 99 and N for 100. If we wanted to use question-specific subscripts, that gets really annoying really quickly when we calculate our test statistic. But I almost forgot to check the conditions. Independence is the first condition. I've randomly sampled, so I can assume independence within each sample. The samples were randomly sampled. So we can assume independence within each sample. But we also need independence between, because we're doing 2 independent samples means t-test, so that's the other condition. And so 0.99 carat diamonds are independent of 1 carat diamonds. Right, we can poke holes in that, but we need to remember that we're arguing that they're independent, right? And so, right, in fact, we're talking about the prices of the 0.99 carat diamonds. Is it independent of 1 carat diamonds? No, but it's an assumption that we're making. 0.9 carat diamonds are independent of 1 carat diamonds. So we can assume independence between. Between samples, right? As soon as we have 2 samples, I have to be able to assume independence within, but also between, unless it's paired data. The normality condition hinges on the sample size, right? If the sample size is larger than 30, then I'm just allowed to assume normality. That's great. But N.99, or I guess I called it N99, a little inconsistent here, is 23. So what do I have to argue? So I assume that the distribution is approximately normal. That's fine. So we must assume, and we can check it with that box plot or a histogram, but we're not going to do that. So we must assume the distribution, oops, is approximately normal. What about 100? The sample size for the 100 pointers or the 1 carat diamonds was 30, which is greater than or equal to 30. So we can assume normality. They're the same, just different ways of getting there. So we may assume normality. Now we're ready to do the test. I need more. Oops. Page. Oop. Eek. There. Sure. Step 2, I call it do the test, do the do. From the formula sheet, T is x1 bar minus x2 bar, technically minus 0, but I don't think I even had it on there. Divided by the square root of s1 squared over n1 plus s2 squared over n2. This is where using those subscripts of 99 and 100 would get really messy. So as long as you've told me, hey, I'm going to use this as my group 1 and this is my group 2, that's totally fine, right? It's just in your hypotheses, I want to see it. So now I have T, it was, I think, 4450 minus 5343. I'll just bring this down, I think. Make a copy. Paste. Okay. Divided by the square root of 1332 squared over 23 plus 1222 squared over 30. Now I'm going to cheat because I have a screenshot already. Just need to find it. There it is. Crop it up. And really make sure when you're practicing and going through these, even though we're just grabbing the T from my calculation here, right? Just make sure that you get the same thing using your calculator, right? Otherwise, what a mess. So T is roughly negative 2.5066. 4 decimal places. The T table has 3 decimal places, so you need at least 3 decimal places. Okay, gut reaction, we can check in. I suspect that I'm going to reject H naught, right? Because I'm 2.5 standard errors below 0. That's far away from 0, right? Using roughly 2 as a cutoff. So we've got this kind of intuition now where we say, okay, this T is quite large into the lower tail, which is what I was expecting, right? Because I want to show that the difference is less than 0, right? Building up to the p-value. My hypothesized difference of 0 is also at a T of 0, and I have a T of negative 2.5066. So this area is the one-sided p-value. Now I can use this to find the p-value in step 3. Step 3, find the p-value. We're going to use the t-table, right? And we need the degrees of freedom. And so using the t-table, right? Tell me that you know which table to use, or because I'm letting you use the z-table, well, not for t's, but the z-table for proportions, right? Tell me which table you're going to use, right? Tell me which one you prefer. And then, but here we've calculated a t, so we have to use the t-table. So using the t-table with degrees of freedom equal to the minimum of n1 minus 1 or n2 minus 1, oops, which is the minimum of 23 minus 1 or 30 minus 1. Why not? The minimum of 22 or 29, well, the minimum of those two is 22. So then I have 22 degrees of freedom. So using the t-table with 22 degrees of freedom, we find, now I'm going to take a screenshot of the table. I think I made a mess earlier here. So I've got my 22 degrees of freedom highlighted already, and I want to find the p-value. Those p-values are down here. This is where I need to remember if I have a one-sided or a two-sided test, and that's way up in the alternative hypothesis. So what I'm going to do is I'm just going to take a weird little screenshot here. Real weird. Let's see here. Copy. Otherwise, it becomes such a huge screenshot there. So I've got my 22 degrees of freedom, and then my one-sided, two-sided p's down here, and we go back up. Oh, what did I say? Oh, I want to know if mu is significant, or if the difference is significantly less than 0, making it a one-sided test. So then I'm here on the one-sided p line. This is kind of a thinking bubble, all right? But here, a continuation of using the t-table with, and then you do your degrees of freedom calculation. This is where if you did it wrong, then I can just follow through, right? We find the absolute value of t equal to negative 2.5066. That's the t that you calculated. The absolute value drops the negative, is between two values. And so I go out here, 22 degrees of freedom, and try to place 2.5066, and I end up somewhere between here and here. So I write those down, 2.183, 2.508. It's a test situation, right? And so it's not terribly uncommon for someone to tell me it's between, 2.508 and 2.819, right? Just kind of rushing through it. That's why you want to have these written down that you're going to be using, right? Because then I can say, oh, well, that's not true, but the rest, your follow through is fine. So then you're safe, right? So the one-sided p-value is between, remembering to write them from right to left, right? Because as your t is increasing into the tail, then the area in the tail gets smaller and smaller, right? And so you want to have your p-value between 0.01 and 0.02. Using software, you can find a more precise p-value, but that's good enough for us. Because now we can state our conclusion. Step 4 is our conclusion. Show off all the things that you know and all the things that you're keeping track of, right? First thing, compare your p-value to your alpha level. So since the one-sided p-value throw that in there. You had to use it, so why not? That it's one-sided. So since the one-sided p-value is between 0.01 and 0.02, we weren't given an alpha level, so the default's 0.05. Okay. It is less than the assumed alpha level of 0.05. What's another way that you could do it? If you wanted to, you don't have to, obviously, because I use the p-value approach always. The other way you could look at it is say, okay, as I move further out, the areas in the tail get smaller and smaller and smaller. What if I force the area in the tail to be 0.05, right? Well, my guys, and by my guys, I mean my p-values were somewhere down here, right? So I've already passed this threshold of 0.05, right? So it is less than 0.05. Could take it one step further and you could say, well, 0.05 actually is when t is 1.717. RT was bigger than that, so then I can reject H naught. That's a lot. But if you prefer that, if that makes more sense, then we can talk about that. But I like to just use one method. Otherwise, there's a lot going on. If it's less than the assumed alpha level of 0.05, which means we have enough evidence to reject H naught, right? We moved far enough into the tail to say, oh, okay, it could happen, but unlikely, which means we have enough evidence to reject H naught. That conclusion has to be in terms of H naught, because we've assumed that the difference was 0 until we had proof, okay, it looks unlikely, right? And if I'm rejecting H naught, then I can say in favor of HA. And you don't have to in favor of HA, because it's more important to me that you only state your decision in terms of H naught, right? Reject H naught or fail to reject H naught. Or you have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. And those are your only two options. If we rejected H naught in favor of HA, then what does that mean? Therefore, and how did there is evidence. There is evidence, and I'm just going to grab the question that I wrote out so I don't have to write it again. There is evidence that the 1 carat diamonds have a significantly higher average point price than 0.99 carat diamonds. Not question mark, period. And that's your conclusion in terms of the question. Kind of wonky, but that's okay. Not gonna fix it. Yeah.
When the alpha level is given, do you still say assume?
No, you don't have to. It's just when it's not given, then I like to emphasize that, hey, I'm assuming it's 0.05, which is standard, but I'm just emphasizing that. But if it says use an alpha of 0.1, you just do that. Nice. Okay. Okay, that's good information. The average point price for 1 carat diamonds is significantly higher than 0.99 carat diamonds. What's a logical follow-up question to that? Well, how much more expensive, right? And so to answer that, we would need to make a confidence interval, right? And so this is the end of this example. We'll do a little twiddle thing. But a reasonable follow-up question would be, how much more expensive are they, our 1 carat diamonds? How much more expensive? I'll use kind of an incomplete sentence there because I think we get it. I'll save it for my confidence interval question. And so to answer this, we need a confidence interval. So, as an example, now I'm gonna really get crazy here. Well, depending on the time it is. Uh-oh. All right, let's get crazy. So what we said, let's use a different color. We had a one-sided test at an alpha level of 0.05. So we put all our alpha in the one tail, okay? Now we know that we could use a confidence interval to test this hypothesis. If the null value is in the interval, then I don't have enough evidence to reject H naught. And if it's outside the interval, I have enough evidence to reject H naught. The problem is when we have a one-sided test, right? Then we've forced all this 5% or this 0.05 into one tail. And so to make a corresponding confidence interval, we would need to pretend that, all right, and can I get a whoop whoop? How do I change the style? Maybe like this. All right. So here it's slightly dashed. I doubled it, so defeating the purpose. Slightly dashed, but I would need to force alpha equal to 0.05 in this tail as well. So for a corresponding confidence interval, for an alpha level of 0.05 for a one-sided test, I'm left with 90% here in the middle, right? I've lobbed off 5% in either tail. And so let me see if I can change this back. Can't remember which one I use. So to construct, oh, it's definitely not that. To construct a confidence interval corresponding to a one-sided test at alpha equal to 0.05, one-sided test at alpha equal to 0.05, we would need to make a 90% confidence interval. We would need to make a 90% confidence interval. It's not terribly important, but there's the off chance that if you made a 95% confidence interval, right, then your conclusion might differ from what the one-sided test does. And so that's why I bring that up. But it's not something that I'm going to test you on, but it's just nice to know. So how about I make the question, construct a 90% confidence interval. Construct a 90% confidence interval for the difference in mean point prices between 1 carat and 0.99 carat diamonds. And maybe I'll sneak this onto the next page. For the difference in mean point prices between, and I'm gonna do maybe in the order that they appear, between 0.99 and 1 carat diamonds. Okay. From the formula sheet, I have x1 bar minus x2 bar plus minus t star times the standard error s1 squared over n1 plus s2 squared over n2. Uh-oh, don't tell me it's that time. It is. Okay. Turbo mode. What do I need? I need my T star. We already know the degrees of freedom. So now I'm going to take my little screenshot and take it somewhere else. Bring this in, copy. And it's the only thing missing. Everything else we have, right? I want to make a 90% confidence interval. And so at 22 degrees of freedom still, right? Because I already did that work and I'm running out of time. So then my T star for a 90% confidence interval is 1.717. Now I did this here, but for a 95, but let's get crazy here. 1.717, change this to 1.7. Like nothing happened there. And then I can screenshot this. Crop top. Wee, wee. So my confidence interval for the difference in the means is somewhere between negative 2.81 and negative 15.04. I guess this is a smaller value. Sorry about that. Negatives. Negative $15.05 up to negative $2.81. We've got this. What's the next thing? Last thing. I have to do my interpretation. We are 90% confident. Oops. Confident, the interval from negative, oops, wait, $15.05 to negative $2.81 captures, and this is where I take for the difference in mean point prices between 0.99 and 1 carat diamonds. So I'm just going to copy that. Captures the difference in mean point prices between 0.99 and 1 carat diamonds. Differences are tricky, right? Because now, depending on how I calculated the difference, right? $15 more to maybe $2.80 more, right? And so per point, a 1 carat diamond has 100 points, right? 99 carat or 0.99 carat diamonds has 99 points. But this is all I'm expecting of you in terms of the interpretation. And with that, I release you. Well, okay, sort of. 7.5 is on ANOVA. I'll post a bonus assignment, but we're not going to cover it in class, and so it's not going to be tested. And so we're done with chapter 7, just like that. If you have any questions, let me know. Otherwise, I'll see you for the test on Thursday.